And let's put some excess charge on it. It's going to distribute uniformly over this outer surface, and we'll just say it has positive charge Q, capital Q. So what do we do with electric field? If we wanted to find the electric field some distance r away from this, how would we do that? KQ over r squared. Right? What's that? That's the electric field from a point charge. Why is it okay to use that? Is it okay to use that? Yes. Because it's a spherically symmetric charge distribution. And if it's spherically symmetric and we are outside of it, we can just view it all as if it's at the center. We did that with mass all the time, right? You had a planet and you wanted to know what the force of gravity between the planet and the satellite was. What did you do? You said the entire mass of that planet was at the center, and you used the distance between the centers, and that's how you found the force between it, right? Because it's spherically symmetric, we can do that. Same with charge. So for electric field, spherically symmetric charge distribution, we're outside. We view it as a point charge at the origin. And this is the electric field from a point charge, and that's the distance between the centers of our objects, right? We good? So what do you think we're going to do with electric potential? What's the electric potential at that point? Right, what did we do with electric field? We said put all the charge at the center, treat it like a point charge. What's the electric field from a point charge? KQ over r squared. So what do you think we're going to do for electric potential? It's spherically symmetric. We're going to treat it like a point charge. Put all that charge at the center and say, if it was a point charge, what would the potential be over here? KQ over r. Okay, I snuck in when you weren't looking. I snuck in the direction over here. Electric field is what kind of quantity? A vector quantity. It needs direction. Electric potential is a scalar. No direction. So normally you'd find that much easier, but we've been beating into you direction, 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 right, with electric fields all this time, vector addition. So now you have to remember that we've got a quantity here where you don't need vector addition. This is a scalar quantity. You just add the numbers together. We'll get there in a minute. Okay. Oh, outside of this charge distribution. So I'm gonna figure out what the electric potential is on the surface of my conductive sphere. So as I get closer and closer to that conductive sphere, R gets smaller and smaller and smaller. My electric potential gets bigger and bigger and bigger because it's a positive charge. And when I get to the radius, capital R, oops. What do I get? KQ over capital R as my potential. So if I were to draw it on a graph, here's my sphere. Here's my electric potential. Oops, that's electric field. I'll do electric field also. Electric field is a function of R. And electric potential as a function of R. So this charge is all distributed over the exterior, right? It's a conductive, solid conductive sphere. The electric field inside that solid conductive sphere has to be what? You see what I'm doing? Here's our conductive sphere. It fills the space around it with an electric field. I'm sort of calling the center of that sphere R equals 0. And I'm going to plot, this is capital R right here. And I'm going to plot the electric field. I'll use blue. So what is it between 0 and capital R? Inside the sphere. Electric field inside a conductor. Say it. Thank you. Man, you guys are killing me. Okay. Then it jumps up and drops off as 1 over r squared, right? So in this region, E is 0. And out here, K Q over r squared, right? Drops off as 1 over r squared. Okay? Does that give you a little bit more visual? Now, the potential. Outside drops off as 1 over r. I'll draw it in red. 1 over r looks like, what does 1 over r look like? Something like this. Okay? What do you think it's going to be inside? At the surface, it's KQ over R. What we have to look at is the change. Did we have it somewhere? Let me see. I think we introduced it at some point here. Yeah, I think we talked about this a little bit. With work done, remember when we talked about work done? And we got the work is Q delta V. And delta V, I think we made this substitution somewhere, is the electric field times some distance. There's actually a negative sign somewhere in here. Anyway, something like that. So we had E there's this relationship. It's the gradient, right? The gradient of the electric potential that tells you the strength of the electric field. So when our equipotential lines are close together, that's the steep cliff, right, on a topographical map. Here it means the electric field's strong. And when they're farther apart, that's the gradual slope on a topographical map. Here it means the electric field isn't as strong. So we've got this, what's important is the change in the electric potential, right? Not the electric potential. So what does this tell us? If E is 0, does that mean that V has to be 0? No. Delta V has to be 0. It means V has to be constant. So when E is 0, delta V is 0, which means V is constant. Okay, that's the important part. E is 0 inside that conductor. That does not mean V is 0, it means V is constant. What constant should we pick? We should pick whatever it is on the surface of the conductor so we have continuity. We don't want it to all of a sudden change. So what is it at the surface? It's KQ over capital R. So we'll just make it continue at that. V equals a constant when E equals 0. And what constant? Whatever it was on the surface. So you can see if I chose a smaller sphere now, and I did the same exercise again, what would the potential be on the surface? I put the same Q on a smaller sphere. What would the potential be at the surface?